Hello, hello. Yeah. So good evening all. Welcome back to PMRFTA ship session from this particular NPTEL course, which is ground improvement. Course is numbered as NSA 23 C78. Myself, Rituras Singh. I am currently working as a Prime Minister Research Fellow in Department of Earthquake Engineering from IIT Roorkee. This course is currently being tutored by Professor Dilip Kaur Bhudia, who is Professor in Department of Civil Engineering from IIT Kharagpur. Those who are joining these sessions for the first time, let me tell you what are these 2 hour sessions particularly meant for. So in this 2 hour sessions we'll plan to discuss to have an interactive session with our learners. We'll also be discussing some of the important concepts which will be required to solve some of the assignment problems. We'll be solving some of the sample questions related to that particular week's content. We'll be also solving some of the doubts related to that particular week. Apart from that, if you are having any other query related to the course, please feel free to discuss. So let's start with the sample questions today. So the first question which is there in front of you, like you need to determine what is the application of the dewatering facility. So yeah, application of dewatering techniques are, so the correct option is all of the above. uh, so basically it's permanently lower the water table for highways. So if you are having the highways at highways the water table at a significant position, so you can lower that down. You can also improve the soil properties, so with the reduction in the moisture content or the lowering of the groundwater table, your strength of the soil can be increased. Also you will be improving the resistance to liquefaction. So once you reduce the groundwater table, so your soil voids can no longer be replaced by the water voids, and in that case you will basically improve the resistance to the liquefaction. So the next question which is there in front of you is like, usually for the typical transverse slope for the shoulder, what is the slope which you will take? So at the shoulder, what is the typical transverse slope you will consider? So again, that's a factual question. So yeah, the correct answer is 4 to 6%. So usually at the payload, the transverse slope which you will see, like this particular slope, is having a value of 4 to 6%. Let's move to next question. Yeah, so there has been a figure which has been shown to you in on the screen. So you need to select what is the drainage application which is represented by this particular figure. So whether it is a trench drain, pavement drain, vertical drain, and the toe drain or toe drain. So let's check the answer. The correct drainage application that represented in the figure below is the drain stream. So with the help of that, you can represent the drain stream. So the correct answer is drain stream. Let's move to question number 4. Yeah, consider the following statement. So you are having two statements in front of you. To ensure minimum water to enter excavation, the drawdown curve should be below the base of the excavation. The drawdown curve can be induced by one side and two side walls. So yeah, you need to select the correct answer. Hello. Okay, sir. Okay, okay. No problem. Yes, yes, yes.
ओके चलो ओके चलो ये सिखाऊंगा। वो सर 5 मिनट में आ रहे हैं, तो आप अगर आसपास हो तो आ जाना। ठीक है ठीक है, ओके ओके।
So let's check the correct answer. Yeah, so correct answer is both A and B statements are correct. So, so here it should be water node to anti-acceleration also. So if this is an acceleration you are having, and this is the drawdown curves for the phreatic level, so they should be below the acceleration. So the correct option is it. And the drawdown curve can be induced by one side and two side also. Yeah, so this can be induced by one side wall as well as the two side wall. So the correct option is option C. Yeah, so let's check the question number 5. You can give a try for question number 5. क्या करवाना है इसमें?
इसमें कुछ नहीं कराना,
हम्म,
ये आ गया इसका।
हाँ, ये बिट्टू का साइन करवाना है। Yeah, so we were seeing the question number 5. So, yeah, the question number 5 is there in front of you. So, in this, you need to select one of the correct option. So, if you want to maintain the bottom stability of acceleration, which particular option you will choose? Overburden stress above sand layer should be lower than uplift pressure. Overburden stress above sand layer should be higher than uplift pressure. Overburden stress above sand layer should be equal to uplift pressure, or none of those. Yeah, so let's check the answer. Yeah, so the correct answer is the overburden stress above sand layer should be higher than uplift pressure. So this can be justified because let's say if you want the acceleration to be stable, so whatever uplift pressure which is offered by the ground in the excavated area, the overburden stress should be higher than that uplift pressure. Let's say the overburden stress which was observed earlier, if it was less than the uplift pressure, so in that particular case, you are basically compromising the bottom stability of the acceleration. So let's move to question number 6. Reshare it again. Yeah. So that's another set of questions. So yeah, in the question number 5, the theoretical solution for rate of flow into well with an unconfined or confined permeable layer can be derived based on which particular theory. So you need to select that particular theory with the help of which you are basically deriving the uh, flow, simulating the flow in the unconfined and the confined permeable layer. Yeah, so the correct option is option B, that is Darcy's law. So Darcy's laws can be used as a theoretical solution. So using Darcy law, we can basically develop the equation for the flow for an unconfined or confined permeable zone. Let's move to next question, question number 6. Yeah, so you are having a job site which requires an excavation of a rectangular area, having area of 200 meter by 180 meter, which the depth of footing is 15 meter as shown in figure. The existing groundwater table is at 5 meter. Below the ground surface is 30 meter thick gravel with permeability of 5 into 10 to the power minus 5 meter per second, which is underlain by bedrock. The groundwater table should be lowered to 2 meter below the bottom of excavation. Deep wells are used to dewater the site. 250 diameter deep wells are used. Given the C dash is equal to 3000, you need to calculate the equivalent radius of the excavation area. So let's check answer for this. So the given area, so you are having a site which is 200 meter by 180 meter. Now you are basically excavating to a depth of 15 meter as shown in the figure. The existing groundwater table is at 5 meter. Below the ground surface is 30 meter thick gravel with a permeability of 5 into 10 to the power minus 5 meter per second, which is having a bedrock underneath. The groundwater table should be lowered to 2 meter below the bottom of excavation. Deep wells are used to dewater the site, which is 250 deep diameter deep wells are used. Given the C dash as 3000, now you need to evaluate what is the equivalent radius of the excavation area. So this can be written as pi r naught square is equals to length into breadth. So we need to evaluate r naught is equals to L into B by pi. Length into breadth is 200 by 180 by pi. So the answer which I am getting right now is 107.07. Yeah, so the correct option is option D. Yeah, so the correct answer is option D, 107. Let's move to next question, question number 7. Yeah, so you need to determine the influence radius of the acceleration area. So right now we have evaluated uh, what is the equivalent radius of the acceleration. Now the what is the influence radius of the acceleration area.
डायरेक्ट करेगा हाँ यार क्लासेस क्या हम लोग हैं?
Yeah, so this particular question is the part of a series of questions. So the main content has been given at top. So you are having a job site which requires an excavation of a rectangular area. The given area is 200 meter by 180 meter, and now you need to excavate this particular depth, particular area to a depth of 15 meter. The existing groundwork table is available at 5 meter below the ground surface. Below the ground surface is 30 meter thick gravel with a permeability of 5 into 10 to the power minus 5 meter per second, which is underlain by bedrock. The groundwater table should be lowered to 2 meter below the bottom of the excavation. Deep wells are used to dewater the site, which is 250 diameter deep wells are used. Given the C dash value is 3000, now you need to calculate what is the influence radius of the excavation area is. So let's check the answer. First of all, you need to consider like till what depth you want your influence zone area is. So you know the height of the water table. Below the bottom of excavation is 30 minus 15 minus 2, which is none other than is 13 meter. So you know the influence radius can be calculated as Ri is equals to C dash. So you need to dewater the site by 250 mm, so that will be 25 centimeter. So you know influence radius is given by C, uh, and the HW node, so where you are using the deep wells to dewater the site, and that is the particular depth, and then you are having the height of the water below the water table again, which is represented by HWI, and then you multiply it with some constant K, right? So C dash we know is given to as 3000. Then HW naught, which you have calculated, is your none other than 25, and SWI is your 30, and then K is your permeability, how much it's 5 into 10 to the minus 5. So let's put it in the MKS, and by solving this the answer which you will get is 254.5 meter. So that is the influence radius of your excavation area. So means, let's say if you are excavating this particular part, so the particular area which will get influence will be in the circular zone, and the radius of that particular zone can be calculated with this particular formulation, which is given by C dash SW naught minus SWI into root K. C dash is your constant, SW minus SW naught. So SW naught, where you will utilize the where you will utilize the some wells, deep wells, to dewater the site. So that will be having the depth of 25 mm, and then your height of the water table below the bottom of excavation, that you need to determine, which is the 13 meter. So that much area you need to capture, and that is into root K, which will be your permeability. So that all formulation is derived from the Darcy law, and that with the help of that you can calculate the Ri, and which is the 254.5 meter. So that is option A. Guys, any doubt in this? Please feel free to ask if you are having any concern about that. Okay, then let's move to question number 8. So now you need to calculate what is the total required discharge is. So let's calculate the discharge. So you are having Q, which is pi k SW naught square minus SW1 square, right? Where you are having ln of radius of influence to outer radius. So let's calculate this. So you have calculated Ri and equivalent radius, so that is 107 meter. Then you have also calculated the influence radius, and then you know SW naught and SW1. So how these formulas came, so you can check the lecture notes of Professor Bedia. You will get like how the discharge calculation is being done. So that is 3.14. Then you are having a permeability with the value of 5 into 10 to the minus 5 meter per second. Then you are having HW naught square. So that is basically given by 25 square minus 13 square ln Ri value is 254.5 254.5, and then you are having outer radius, which we have calculated, that is the equivalent radius, which is 107 meter. So that is the discharge calculation. So what is the value we'll get from this? So let's see. Let me check it again. That is the ln, yeah, 3.14 into 5 into 10 to the power minus 5 into 25 square minus 13 square ln divided by 254.5 divided by 107. Yeah, so the answer which we get 0.00826. Yeah, so that is the answer. If you are having any concern, please let me know, we can discuss that. So it's basically you can utilize the Darcy law, and once you are having a proper diagram like how the equivalent radius and your radius of influence is basically affecting the flow inside your excavated ground. So in that case you can calculate how your discharge is basically taking place. So it has been derived with the fundamentals of the Darcy's law, so you can utilize that and calculate the flow into the ground. So your Q value for that particular part is calculated using this particular formulation, which has been derived again by Darcy law, and then with the help of that you can calculate how much discharge is being taking place. So let's move to question number 9. This was the total required discharge, and now you need to calculate what is the discharge of each values. So we need to calculate what is the discharge for each value. So if you will check the total, the radius for well I used to dig out to the side, which is having the 250 mm diameter deep well. Yeah, so now you need to calculate how much discharge in each well is happening. So you can utilize the same equation. So you have been given with the diameter of the well, which is the 250 mm. So you can calculate the radius, which is by 2. Influence radius you have calculated, which is 254.5. So now we can evaluate the discharge of each well, which is given by Q is equals to pi k HW naught square minus SWI square, which is ln Ri by R naught. So 3.14 into 5 into 10 raised to the power minus 5 HW square minus HWI square. HW naught is 25 square minus 13 square. Your ln of Ri, Ri is 255.4 is 5, and your sorry, it's 0.125 that we need to take the radius of the valve. Here you will take the 254.5 and then you need to calculate. Ri is basically your influence radius, yeah, and R is your well. So again, sorry, that will come inverse, so that will be 254.5 by 0.125. I'm again sorry. So you can evaluate this particular results. So 25 square minus 13 square, answer into 3.14 into 5 into 10 to the power minus 5, answer divided by ln 254.5 divided by 0.125, which is none other than the answer which you will get is 0.0094. Yeah, so that is the discharge of each well, which is Q is equals to 0.0094 meter cube per second. So let's move to question number 10. Yeah, so now you need to evaluate what is the number of deep wells required to to extract the water from the ground. You have calculated the total discharge. Now you have also calculated the discharge which is happening in each well. So accordingly, you can calculate what is the number of deep wells which are required. So let's calculate this. What are the number of defects required? So you have calculate total discharge discharge from each well. So your total discharge which you have calculated is 0.0094 meter cube per second, and here it's 0.0826. Okay, so total discharge is 0.00826 and discharge from each well you have calculated is 0.0094. So now let's check the answer for this. So 0.0086 answer divided by 0.0094, which are 8.78. So number of deep wells is 9 wells. So total number of deep wells required is 9 wells. Let's move to question number 11. If you have any doubt, please feel free to ask. Okay, then let's move to question number 11. Yeah, so the typical transfer slope for a payment is, so in our previous first question we have seen like what is the typical transfer slope for a shoulder is. Now what is the typical transfer slope for a payment is. You can refer the lectures of Professor Bedia, you will get the value there. Yeah, so please give your answers in the chat box. Yeah, let's check the answer. Yeah, so the correct answer is 1.5 to 4 percentage. And the typical transfer slope which we have seen for the shoulder was around, okay, that was another question, but yeah, it was around 4 to 6 percentage. So for payment is 1.5 to 4 percentage, and the for shoulder is 4 to 6 percentage. Okay, we can skip this. Yeah, so coming to question number 13, the correct option about applications of drain from the following option given below is, so why do we use drain for? So you need to select one of the particular option. So let's check the answer. Yeah, among all these four, so definitely we are not using drains to deaccelerate the consolidation. Rather than that, we are using drains for accelerating the consolidation. So that is the wrong. Okay, we are basically using the drains for minimizing the soil expansion. So with the help of the drain, we are basically preventing the soil particles to expand. So yeah, we are using it for minimizing soil expansion. We are also using it for increasing the uplift force. So yeah, all of the four options are correct. Sorry, we are basically reducing the uplift force. So with the help of the drains, we are decreasing the uplift force, because you won't be having the pressure from the hydrostatic pressure which is offered by the uh, excess groundwater available inside the ground. So you are basically reducing the uplift force, and definitely if these two are wrong, so option D can't be correct. So the only correct option is minimizing the soil expansion. So some people have given answer. Yeah, we are not using it for decelerating the consolidation. Basically, we are using the drain for accelerating the consolidation. So the only option which we can go for from this all four is minimizing the soil expansion. So that is one of the application where you are using the drains. Coming to question number 14, so you need to select the correct options about dewatering methods from the following options given below. So you need to so let's check the answer. Yeah, so the correct answer is option D, all of the above. So yeah, for the dewatering methods, we are using the well punch methods. So we are using the wells to extract the water. We are also using the electroosmosis process, where we are using some electrochemical reactions to extract the water. We are also using some of the pumping techniques to extract the water, which we also call it the sumps. So all those three methods we are basically using it for the dewatering method. So The correct options among all those four is all of the above, because all of your three above options are correct. Moving to question number 15, considering the following statement, you have been given with the two statements. The first statement is a conventional well point system dewater soils that can be drained by the gravity flow, such as gravel. Then you are having the second point, vacuum well point system dewater soils with low permeability, such as silt. Among all those two statements, which of the statement you would like to go for? So, is it a statement A or a statement B? Yeah, it is. So let's check the answer. Yeah, so the correct answer is option C. Both statement A and B is correct. So what is the first statement? So statement first basically tells you like wherever it is possible, you can utilize the gravity flow, which basically allowing the drainage to happen through the soil. So the conventional well point systems basically de-water soils that can be drained by the gravity flow, such as gravel. Then you are having vacuum well point system, which basically de-water soils with low permeability, such as silt. So yeah, the correct option is C. Both statement A and B is correct. Moving to question number 16. I think we have already done this. Let's move to next question. Yeah, so that's a similar type of question which you have seen. So you can utilize the same formula to calculate this. But yeah, here you need to evaluate the coefficient of the permeability. So we are having a confined aquifer. It's a confined aquifer. It's having a 5 meter thick which is 5 meter thick, that gives a steady discharge of 27 liter per second through well of 4 meter radius. The height of water in well was 12 meter above the base before pumping dropped to 8 meter, and radius of influence is 300 meter. You need to evaluate the coefficient of the permeability in meter per second. Yeah, so we know for the confined aquifer you are having the discharge which is given by 2 pi d h minus h ln r by r. So permeability then can be obtained using q ln r by r 2 pi d h minus h. So your q is 27 liter per second, so if converted into meter per second 0.027 ln r by r, which is 300 by zero point 0.4, it's your 2 pi, and your diameter is 5, and then your h minus h. So your h minus h is basically 12 minus 8. Yeah, so with the help of this you can evaluate how much is your permeability. So k, so your k value then can be obtained as 0. So let's see how much value you are getting. 0.027 into ln. So yeah, the answer which I'm getting right now is 1.423 into 10 raised to the minus 3. Yeah, so q has been given to you is in meter cube per second, then 2 pi, yeah, and diameter which is given to you is 5 meter, and h minus h you is given 12 minus 8, so you are obtaining the 1.423 into 10 raised to the minus 3.
So the coefficient of permeability is 1.42 into 10 to the power minus 3. Yeah, so here it should be 10 to the power minus 3. So the correct option is option B. It should be is there in the order of 10 to the power minus 3, which is not given to you. Yeah, so again it was straightforward. So you just need to know like what are the derivations which are associated with the confined aquifer and unconfined aquifer, and how you are basically calculating the discharge through all of them. So once you will calculate this, you will come to know how we can utilize those discharge values for the calculation. So that was the part. So that's how you can calculate the coefficient of permeability utilizing the same formula. So yeah, so that's it for today. That was the final question for the day. If you guys are having any doubt, those who are watching this video at the latest stage, you can post your queries in the comment section of the videos which have been posted, and we'll address your query over there. And that's it for today. Thank you so much for joining. We'll meet on next Tuesday at same time.